Okay, so now we'll consider symmetries to reduce the reachability graph. Up to now, you know about symmetric nets and their syntax and semantics. You have an intuitive idea of symmetries, of how symmetries work in symmetric nets. And we'll study formally these symmetries, their use for the construction of a reduced reachability graph. So let's consider a symmetric net, N, with a set of places, transition, color sets, pre and post conditions, and an initial marking M0. And we consider a set, capital S, of symmetries, so S1, etc., Sn, where we associate with each unordered class Ci the total permutation group Si. And for each ordered class Ci, we associate the total rotation group Si. So S is the set of symmetries of a net N. So permutations and rotations according to the class that are unordered or ordered. So these symmetries have quite useful properties. If we have a symmetry and a function, a color function, that are, well, these color functions could be identity of an element, or the broadcast function, or the successor function. Well, we have a commutation of the symmetry and the function. So if we apply one first and the other afterwards, it's the same as doing the other way around. So we can define an equivalence of on markings according to the symmetry. So two markings M and M prime are equivalent according to the set of symmetries S. If and only if you can find a symmetry such that M prime is obtained from M by applying this symmetry. For each marking, we define its marking class, which is also called an orbit, with respect to the symmetries S, and we denote it by M in brackets and S as an index. So this marking class is the set of markings M prime, such that there exists a symmetry that gives from M this marking M prime. So it's all the markings that can be represented by M and that are obtained from M by applying a symmetry. So M in brackets, well, the equivalence, the marking class is a set of markings containing all equivalent markings. Now when we have a transition T with a color CT, that is enabled in a marking M, we also have the transition T with the color CT to which we apply a symmetry S that is enabled in the symmetric marking SM. So if you can fire a transition, if it's enabled, you can apply the symmetry, same symmetry to the marking and to the color for firing the transition. And the result is still valid. So here you have the proof, and if you can, well, if you read the details, you can see it's quite simple. You start from saying that the marking must be greater than the weights, the preconditions of the transition. You apply the symmetry to the both parts of the inequation here. And then since you can apply the symmetry either outside or inside the function, well, you repeat the rewriting of the rules and you obtain exactly the firing for T as CT. The firing, of course, well, they are enabled, but the firing gives the symmetric marking, so it's the same, and it's a similar kind of proof that we have here. So if you have a marking M in which you can fire T with a color CT giving a marking M prime, well, you can equally well start from a symmetric marking of M, Sm, and phi transition T with the symmetric colors SCT, and obtain the symmetric marking of M prime as M prime. So the proof is here, it's similar and quite easy. Okay, so now at this stage you know about symmetric nets, their syntax, their semantics. You know the formal definition of symmetries in symmetric nets, the formal definition of markings, and their firing equivalences. These notions will be used in the next sequence in order to derive automatically a quotient reachability graph in order to reduce the reachability graph.